Welcome to Ask and Learn.
We're asked to prove that there exists a non-negative integer n such that the n equivalence classes of M are the same as the n plus 1 equivalence classes of M. This is the first part. So to prove this, let M be a deterministic finite state machine with n states. Let E be an n equivalence class of M. And let A and B both be states in E. Then, by definition, we have that A is n related to B. And so f of ax and f of bx are both non-final for every input string with L of x less than or equal to n. And now let y be a string of length at most n plus 1. Well, this actually has two different cases. Suppose that y is a string of length at most n. Then clearly, we already know that f of ay and f of by are both final states or are both not final states. So let's suppose instead the length of y is equal to n plus 1. Now, since the length of y is greater than the number of states, by the pigeonhole principle, there is a state that is visited at least twice when the input is y. So it follows that there are two strings y1 and y2 such that y equals y1 and y2. So y is a concatenation of y1 and y2. Neither string can be the empty string also. And we have that y1 ends in the same state as y. Now y1 has a length of at most n. So it follows that f of a y1 and f of b y1 are as above. And therefore, since y and y1 end in the same state, it follows that f of ay and f of by are as above. That is, they are both final states or they are both not final states. And so we've shown this in both cases for y, so it's true for y in general, where the length of y is less than or equal to n plus 1. So I'll write this out. So f of ay and f of by are both final or non-final. For all strings y, such that the length of y is less than or equal to n plus 1. And therefore, it follows that a is n plus 1 related to b. And therefore, it follows that E is an n plus 1 equivalence class of M. So that was the first thing we needed to prove. The second thing we need to prove is that the set of n equivalence classes of M equals the set of star equivalence classes of M. So again, we have that M is a deterministic finite state machine with n states. And again, E is an n equivalence class of M. And finally, let A and B be elements of E. So they're both states in E. Therefore, we have that A is n related to B. And then by the definition, it follows that f of ax and f of bx are both final or both non-final for all input strings x with a length less than or equal to n. And now let y be a string of length k. So if y is a string of length at most n, that is, k is less than or equal to n, then we already know that f of ay and f of by are both final states or are both not final states. So instead, let's assume that the string is of length k greater than n. Now, since the length of the string y is greater than the number of states n, by the pigeonhole principle, follows that there is a state visited at least twice when the input is y. And so, just as before, we can find two strings, y1 and y2, that are non-empty, such that y is the concatenation of y1 and y2, and we have that y1 has length at most n, and the string y1 ends in the same state as the string y. Now, since y1 has a length of at most n, it follows that f of a y1, f of b y1 are both final or non-final, and since y and y1 end in the same state, it follows that f of a y and f of b y are also both final or non-final. So now, this, in addition to the proof where y has a length less than or equal to n, shows that f of a y, f of b y are both final and non-final, or non-final, for all input strings y with a length of y less than or equal to well, the length of y is arbitrary, and this implies that A is star related to B, and therefore we have that E is a star equivalence class of M